So our final topic for today is going to be a check of how to find out whether f is a gradient vector field. We've already talked about one way of doing this. One way is to try to work backwards. Starting with our f, we can take our integrals of each of the components with respect to whatever respective variable it is to work backwards to try to develop a potential function. I'm going to give you a quick check as well. So this is our quick method. Recall that our vector field, if it is a gradient vector field, as a function of x, y, and z, I'm going to do the big case, and then we can look at smaller cases. Typically, we denote that as having a first component function, a second component function, and a third component function. Recall that because for all gradient vector fields, we know that the gradient of phi is exactly equal to f1, f2, f3. And what does that give us? That gives us that my partial derivative of phi with respect to x is equal to f1. That also gives me that the partial derivative of phi with respect to y is equal to f2. And the partial derivative of with respect to z has to be equal to f3. This is just review. This is just notational review. And I want to, in the back of our heads, somewhere way back in the day, we talked about Clairaut's theorem. Clairaut's theorem tells us that our mixed partials always have to be equal to each other. And because phi is just any old function, and in particular it's a continuous function, it means that its mixed partials have to be equal. So if I take the derivative of this with respect to y, maybe you don't like this notation, but I like this notation. These are my partial derivatives with respect to y. This is the same thing as phi of xy, which is equal to the partial derivative of my first component function with respect to y. That better be equal to the partial derivative of f2 with respect to x, because that's exactly, this partial derivative is going to be phi of yx, which is equal to the partial derivative of f2 with respect to x. So what did we just say? So if f is a gradient vector field, then it must be the case that the partial derivative of the first component function with respect to y must be equal to the partial derivative of the second component function with respect to x. But this generalizes. This has to also be true for every other pairwise combination of these. So if I were to write all this out, and I'll write it out as a lengthy formula, this is my messy scratch work. Really what we're saying is the partial derivative of our first component function with respect to y has to be equal to the partial derivative of our second component function with respect to x. That's what I just have written there. The second check is that the partial derivative of our first component function with respect to z has to be equal to the partial derivative of our third component function with respect to x. How am I coming up with this? Well, I know that f2 is the partial derivative of phi with respect to y. So this is the combination that's taking care of phi of xy, meaning my partial derivative of my phi function, my potential function with respect to x and then with y, or with respect to y and then with x. And these are just two different ways of writing that. Similarly, these are just two ways of writing my partial derivative of my phi function with respect to x and z. And finally, I have one last set of equations. It's my partial derivative of the second component function with respect to z must be equal to the partial derivative of my third component function with respect to y. Because these are the mixed partials with respect to y and z of our potential function. So if, I should write this as an equal sign, if all of these things are equal to one another, then we know that our function is in fact a gradient vector field. And if one of these things happens to not be equal, then we know it's not a gradient vector field. This may seem like a lot of checks, and maybe it is, but suppose that we only had two components. I wrote this out in generality with all three of them, but if I just had a function of x and y, this is where we'll get easy. If I just had a function of x and y, then I don't have to worry about this third component function. And it means I don't have to worry about my xz check or my yz check. That all I have to check is that the mixed partials of these two guys are equal to one another. And that actually is a really quick, easy check. Let's go ahead and see an example. So let's check out an example where we use our tricky way of evaluating whether or not f is a gradient vector field. And let's let our f function in this case be given by y squared in the first component, 2xy minus 3z in the second component, and negative 3y in the third component. And we want to check, sort of my mental marker, I'm going to think of phi of xy. So I want to check the partial of the first component with respect to y and the second component with respect to x. So let's check out what those look like. I just said I want to look at what's the first component function, the partial derivative with respect to y. And in this case, it's going to be equal to 2y. That's something easy to compute. And now I'm going to look at the partial derivative of the second component function with respect to x. And when I take that partial derivative, I'm treating y as a constant, and I end up with 2y, which is great. That means that these components match one another. But we haven't yet verified that f is a gradient vector field. We have to make sure that all of these partials match. So our next set of partials, I'm going to look at xz. And so that's the partial derivative of my first component function with respect to z. And in this case, that's just 0, because there are no z's in there. And then I'm going to look at my partial derivative of my third component function with respect to x. And that's also 0. So that's great. That one matches as well. My final mixed partial that I have to check is the mixed partial, my potential function with respect to y and z. So that's going to be my second potential, or my second component function, the partial derivative with respect to z, because this part is the y part, and the z corresponds with the c. So it looks like this term is just 0, but negative 3z becomes negative 3. And then finally, I'm going to check the partial derivative of the third component function with respect to y, and I also get negative 3. Da 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 da! So we just found out that f is a gradient vector field, which is great. It means that we can apply the fundamental theorem of gradient vector fields. The downfall, we just did all this checking, right? The downfall is that we still haven't actually found out what that potential function is. And we need to use that potential function in any case that we're evaluating a line integral that isn't a closed line integral. So even though this is a quick check, and sometimes it's faster than others, it may not be the end of the story, that we might have to go back and still assess what is our potential function. And actually, for the sake of review, let's work through finding the potential function for this particular example. So to find the potential function, recall, it means that we're going to have to integrate each of these terms with respect to whatever variable they are. This is saying that my potential function's partial derivative with respect to x is exactly equal to y squared. So I'm going to integrate both sides with respect to x, and I find that I get out, what is that, xy squared plus a constant function that could include both y's and z's, because we were treating y's and z's as constants. So that's the first function I get out. Next, whoops, I know that my potential function's partial with respect to y has to be equal to this long chunk, 2xy minus 3z. And I'm going to integrate this long chunk with respect to y, because it's in the second component. And when I take this integral with respect to y, I'm treating my, oops, this should be a z. Sorry, that was a miscopy. So when I take my integral treating x's and z's as constants, it means that this becomes y squared, and it cancels with the 2, so I end up with just xy squared, which is great because it matches up here. And then I get a minus 3zy term, and then I get plus some constant that could be a constant of x's and z's. Finally, when I integrate, finally, I know that my potential function, the partial derivative with respect to z, has to be equal to this final term, which is negative 3y. And I'm going to integrate both of these, holding both x and y as constants. I'm integrating with respect to z. In this case, my negative 3y I just treat as a constant, and so I end up with negative 3z y, negative 3yz, plus some function of x's and y's. And now we get to do our matching game. And I'm going to highlight, we see that our function of x's and y's in this case, I'm going to circle all in red. This is a function of x's and y's, this is a function of x's and y's, and it matches with this term, the function of x's and y's. So we know that that's a term that's in our potential function. Additionally, we have this term that's a function of y's and z's, which matches this term, which is a function of y's and z's, which matches this term, which we said was a constant function of y and z's. And it turns out that in this case, our function of x's and z's just doesn't exist. There isn't a term that's just x's and z's in our potential function. So this, it turns out, is just going to be equal to 0. And it means that our potential function in this case, after all the things that I circled, or up here, we just found out that our potential function of x, y, and z is going to have a term that has xy squared in it. It's going to have a term that has negative 3yz in it. And then this function of x's and z's doesn't actually exist, but it could have some constant on the end. It could have some constant term. And we can, in our head, really quick check, what's our partial derivative of this with respect to x? It is, in fact, y squared. Our partial derivative with respect to y is, in fact, 2xy minus 3z. And our partial derivative with respect to z gives us a negative 3y. Our partial derivative of our k will always go to 0, and so that's why our k can be there. And we see that this is, in fact, the potential function that matches for this particular gradient vector field. Thanks, that's it for today.